Everything else seems to be working out just fine. I'll keep my 10 increments should be sufficient. I can go into finer increments if I want to, but 10 increments will be sufficient for what we need to do. So far we've applied loading in only one direction. Now what I want to do is subject this same to strains in the longitudinal direction and to strains in the transverse direction. Both of them are equal to 0.01. I really want to subject it to a state of biaxial plasticity so that I can better understand what the Prandtl-Troyer simulations are going to show. Those are the ones that have been programmed into Abacus for the elastic, perfectly plastic EQ. So in order to look at that, I want to subject this analysis to biaxial plastic strain of 1%. How should I go about doing that? There are different ways I can do this, but I'm going to pick a slightly simpler way. I'm going to take that original node that I had constrained to be only in the one direction, and I'm going to include I'm going to constrain that whole vertical edge to have U1 equal to 0. So what I'm doing is now I'm looking at a situation where that plate, shear wall, planar element, whichever way you want to look at it, is now restrained to U2 along this edge, and it is restrained for U1 along this edge. Which means that when I subject it to a displacement increment of 0.01, it should work out because I've got adequate boundary conditions. Which means that my second step when I applied the loading, I need to edit that. Can I edit that to include the U1 along the vertical edge? Probably not. Which means that I'll have to create a new new boundary condition, and it will also be applied in the same step, step number 1, and it will be applied along the vertical edge, and it will say apply the U1 of 1.2 inches. Why 1.2 inches? Because it's a 120 inch long and I'm applying a 1% strain. And there it is. I'm creating some of the simplest models for the world of plasticity. Right now I've got a biaxial loading case applied. And they're both being applied in the same step. I'm applying proportional loading, so to speak. The strain will reach 1% over that one step in 10 increments, and it will be a proportional loading. Why am I saying it's going to be a proportional loading? They're applied in the same step. If I wanted to apply 1% plastic strain first in the vertical direction, and then apply a 1% plastic strain in the x direction, they would have to be two different steps. I would have to apply them one after the other. But I'm going to do that. I will do that as well. That will be the next analysis I do. Right now I just want to continue with the proportional loading criteria. And if you look at, they're being applied, the amplitude is ramped, which means that it's being applied slowly over that, it's being applied in slow increments along that step. At the end of the step, they will both be at a strain of 1%. The loading is still off. I'm not applying any specific loading. I can create a new job. I'm providing some information so that if I have to come back to it, I'll know what the results are. And I'm submitting that now. Well, it should take only a few seconds. These problems are too simple to need any more time. In fact, if you look at it, all the elements, the way we've defined the model, it's an idealized model. Each and every finite element has the same state. It's not like the state varies in the x or y direction because we're doing an idealized analysis. Really speaking, I don't need a very fine mesh. I could do this problem with a mesh of one element if I wanted to. But right now we've defined the mesh size, so we might as well keep it. The answers are not going to vary depending upon the mesh size at all, because the problem is an idealized loading condition. There we go. So we've now got all the analysis steps. It's once again done 10 increments like I'd asked it to do. And now we can start looking at the results. We can start off by looking at multiple plot states. It's telling me that I have applied a permanent displacement of at least 1%. If I look at my, it seems to want to show me the von Mises stress first. I don't know what the von Mises stress is, but it wants to show it to me first. And it turns out to be equal to always 50 Ks. I will talk about what that means a little bit later. What was the yield criterion? Is that the yield criterion that we are working with? J2 minus the uni-axial yield stress squared divided by 3. Is that right? This also means that the square root of 3J2, J2 is a scalar quantity, right? It's just sigma x squared plus sigma y squared plus sigma z squared and all that. It's not a vector of any kind, it's a scalar quantity. So if I take the square root of 3J2, that's going to be a number. And yielding will occur whenever that number, square root of 3J2, becomes equal to the uni-axial stress sigma. Is that correct? This is what it's calling as the von Mises stress. So it's trying to tell you that the von Mises stress is 50. That's what it's trying to tell you. It's the square root of 3 multiplied by J2. It's trying to tell you that, hey, I solved this J2 problem and it was always that the von Mises stress was always equal to 50. In fact, if I'm sitting on the yield surface, that had always better be equal to 50, right? Because my yield surface is defined by the fact that J2 is equal to sigma y squared divided by 3. So it's telling me that the von Mises stress is equal to 50 Ks. What is the von Mises stress? It's some scalar quantity that represents the effective stress at the material points. Why does it represent the effective stress at the material points? Because you could have different combinations of S11 and S22 and so on. And your yield criterion, the von Mises yield criterion, says sigma 1 squared plus sigma 2 squared minus sigma 1, sigma 2 has to be equal to sigma y squared. In 2D space, this is what it says, where all of these are principal stresses. So what it's telling you is that since the point has yielded, it wants to show you that the von Mises stress, which is plotted in sigma p1, sigma p2 space, is always on this ellipse. And whenever it's on this ellipse, the square root of 3J2 will be equal to 50 Ks. And that's why it wants to show you. It understands that you're in the world of plasticity and wants to show you the von Mises stress, because that's the effective stress. You can have many different combinations of sigma p1 and sigma p2. It understands that you may have different combinations of sigma p1 and sigma p2. For example, in this example, if you look at S22, it is equal to 50 Ksi. If you look at S11, it is also equal to 50 Ksi. Oh, wait a minute. What happened here? I subjected it to a loading that was proportional and biaxial. And it's telling me that sigma 11 is 50 Ksi, sigma 22 is 50 Ksi. Does that make sense to you? Yeah? How? I thought yielding occurs when sigma 1 is 50 Ksi or sigma 2 is 50. So how did it happen that sigma 1 and sigma 2? Well, if you're looking at the von Mises ellipse, this is the loading axis that I took. Proportional loading. And if this point corresponds to sigma y, and this point corresponds to sigma y, then this point corresponds to sigma y, sigma y. So when you apply biaxial loading to the steel plate, the yield stress in both directions, or yielding will occur when sigma p1 and sigma p2, or S11 and S22 are both equal to 50 So it's telling you that, hey, I found it to be the same. These are the answers. But it wants to show you the von Mises stress because that will always tell you where you are in terms of the yield criteria. Tells you the square root of 3 multiplied by J2. It tells you what the effective stress is. It just calls it the von Mises stress. And if your von Mises stress is greater than 50 ksi for an elastic, perfectly plastic material, you should run out of the room. Because it's not possible for plastic. That means that that software is pulling a fast one. Right? It's trying to tell you something that is impossible. So nobody can fool you now because you'll always be able to look at the effective stress and see if it is satisfying the J2 material criteria. Because that's what we did. We programmed a material that has J2 dependency, which means that if it is yielding, the square root of 3J2 will always be equal to 50. Whatever it is that you specified in that tab as 50, 0. If you had specified 55, it would go up to 55. So that's the first thing. That's the effective. Now if I start looking at the strains, what I find is my E11 is 1%. That makes sense. I'd applied that. E22 is also 1%. That also makes sense. I'd applied that. Now if I start looking at PE, and I look at PE11, I'm looking at a strain of 8.79 multiplied by 10 to the power minus 3. And if I look at PE22, it's got the same value, 8.73 multiplied. Does that make sense? Well, if I remember this right, the normal to the surface will be along that 45-degree line, which means that the projections of the two plastic strains will be the same. But this problem is too easy. This gave me things that are not really teaching me anything. What I really want to see is I want to apply a loading condition that will reveal to me that it is following the stress states move on the ellipse. That's really what I want to see. And I want to see how those plastic strain increments are following the Prandtl-Royce relations, which have disappeared. What are S11 and S22 in this context? They're not the S11 and S22 that Abacus is talking about. Those are the deviatoric stresses. Which means that they are the actual stresses minus the pressure. What is the pressure? There's too much pressure. I can look at the pressure. I'm looking at the stresses. When I select the option for stresses, look at all the options that it's giving me. It's telling me, would you like to know the von Mises stress, which is the square root of 3J2? It wants to reveal that to me if I ask it. It wants to show me all the principal stresses, but it also wants to show me the Tresca stress. I wonder what the Tresca stress is. The Tresca stress is sigma 1 minus sigma 2. That's the maximum shear stress. According to the Tresca yield criterion, yielding occurs when the modulus of sigma 1 minus sigma 2 becomes maximum and it is equal to 50 ksi. Of course, the Tresca stress is also equal to 50 ksi, sitting on that yield surface. It also wants to show me what the pressure is. So I can always ask it, what is sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 divided by? And it will show that information to you. And I can also look at the third invariant. I would not know why I was looking at the third invariant, but it would show it to me in case, like I said, Abacus will give you the group to So it does give you the third invariant also as an output. Now if you're working with a hydrostatic pressure dependent material, then you will definitely want to look at the values of pressure. You'll definitely want to look at the values of J2, the von Mises stress. So what? It gives me the first invariant, which is pressure, the second invariant, which is the third invariant, directly. Why doesn't it give me the second invariant? It tells me I gave it to you right here. I gave you J2. So you can use that information in order to get your second invariant. All right. So the pressure is going to be, I really want to be able to see, yeah, these were the Prandtl-Royce relations. And S11 and S22 were equal to sigma 11 minus sigma m and sigma 22 minus sigma. It so happened that for the proportional loading case, sigma 11 and sigma 22 are equal. Sigma m is also equal to E, are also equal, which means S11 and S22 are equal. It's really proportional loading, and therefore d epsilon 1 P and d epsilon 2 P are equal. So when I integrate it all, I get the same plastic strain whether I'm looking at the 1, 1 or the 2, 2 dimension. So I really need a better example in order to investigate how the yield stresses are supposed to move on this path. Right? That was the first condition. The yield criterion or the consistency condition requires that the yielding point will always move on the one Mises ellipse, and that the flow rule says that it will always be perpendicular to the Mises ellipse. So I need a better example in order to investigate that, and I need to post-process that example a little bit. So what we're going to do is we're going to look at non-proportional loading. Next time, we'll take a look at non-proportional loading, where we'll apply yielding in the one direction first, and then we'll stretch it in the 1 and 2 direction together, and we'll post-process all of that information to reveal what these directional voices are.